היית בהתחלה של הצד של... לא בהתחלה, כאילו רחב.
זה נפל, זה לא מוכיח כל פעם שצריך הדבר הכי שאתה יכול להגיד שאתה נפל. אתה לא יכול להגיד שזה איפו, כאילו די בדיוק.
אל תמרחי משהו.
אז כל הקשות וכזה. מחר עם
הנפל, אתה בדיחה כלשהי.
מערב, לא חומר, זה בדיוק נפילה לוגית.
שיסתדר לך הקט כפול קצב. הקט כפול קצב, טריגר צייפל.
הוא לא הגדיר את זה.
לא, זה... כי הברא והקט אין להם שום משמעות, זה רק פורמליזם מתמטי. מה, אבל התורת תקופות זה פשוט מדהים הדבר הזה.
כלי ממש טוב.
אני מנסה לשאול טריידינג במשהו שאני יכול לעשות אותו בפרויקט השנה.
בעיית הסיבתיות זה לקרוא את אדם שסיבתית היא עד נפל בשחור שחור אדם יכול בוי בעדוי וגם
אבל אז יש משהו כמו אפקט הארוניקו, שמראה שבאמת יש איזשהו פוטנציאל כלשהו מרחבי, שגם כשאני לוקח איזשהו מטען שכביכול לא אמור להיות מושפע מכוחות, הוא עדיין מושפע מהפוטנציאל שיש לי מסביב למשמעת אם יש לי משרן כאילו זרם, אז יהיה מסדר אם אני לוקח איזשהו מיטה קטן וזורק אותו לסביבה, אז הוא יהיה מושפע בגלל הפוטנציאל שיש מתחורות, הפוטנציאל כן נמצא מחוץ לכל המעלה, שלא הציץ את הרמה. רואים שכביכול עדיין יש השפעה מהפוטנציאל, לא בלי איזה מבחינת.
כאילו חמוד את זה ידן? כן? אתה נתק משהו ידן. נתק את הכבל. כן, אני סבבה לזה את הכבל. תחזיר אותו בסוף השיעור.
All right, so we're starting the lecture. I will remind you that the last thing that we developed yesterday was the ergodicity assumption. Ergodicity assumption or hypothesis. Okay. And basically what it means we developed it for the energy, but it can be developed for any kind of observable. So we follow the energy as a function of time. And as a function of time, it fluctuates. And it is actually going from one state to another, etc., 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 etc. We can also say, well, we don't have to follow energy. We can follow, for example, the magnetization of the system. Okay, so here we will have M as a function of time, and it will also show us some sort of maybe fluctuations. All right. Now, there are two kinds of averages that one can perform. The first kind of average is just to follow this trajectory as a function of time, register all the possible outcomes that we measured, and we can say that average E equals to 1 over number of measurements that we have performed, right? Sum over I goes from 1 to n, E measured at time ti. Okay, E at ti. This is temporal average. Okay? You follow the trajectory, you follow your observable, you register all the different outcomes, you sum up everything that you have measured, you divide it by the total attempts, measurement attempts, and this is the regular average that we know. On the other hand, we have a different kind of average that you have been taught in probability and statistics class, which is this kind of average, which is ensemble average. Okay, so this is temporal average, and this is ensemble average. And the difference between them is that this guy, you don't follow any trajectory, you don't have any ingredient that is related to time. The only thing that you have to know is what are the different states in your system, energetic states, and what are the different probabilities of those states. Okay, so this is the usual stuff. So this is P, I, Pj, Ej. Sum of j, so here, summation over different states. Different states. Here, the summation over different measurements. The ergodicity hypothesis states that temporal average is equal to ensemble average. So whatever we are measuring in experiment can be calculated. So the same goes for magnetization, right? We follow exactly the same formalism, and we can write down that the ergodic hypothesis is a equality between temporal average and ensemble average. For the magnetization, it will look like this. Left-hand side can be obtained only in experiment. The right-hand side can be obtained by theoretical calculation. Ergodicity hypothesis states that, well, any prediction, so anything that you observe in nature, right, you can calculate by the means of the knowledge of the different probabilities, statistical probabilities of the different states of the system. Okay? It is not always applicable. Maybe we will talk about it by the end of this class, not today, of the semester, but not all the systems around us satisfy ergodicity hypothesis. It's sometimes broken, and those are very interesting instances when this stuff does not work. But for the purposes of this, for almost the whole semester, we will assume this ergodicity assumption. Now, Why it's so good? Because, well, this is very nice starting point. Okay, so anything that we want to compute, all the averages that be used in thermodynamical description can be actually obtained by the knowledge of the different states of the system, the probabilities of occupying those states, and the values of the observable for each state. So for example, for magnetization, it's going to be summation I over the same pi mi. Right, so let's do it J. Great. Now, but this is still not good enough. Why it's not good enough? Because I was trying to impose onto you that this world is very complex. We have many particles. We have a lot of interactions, etc., etc., etc. And it's actually impossible to exactly calculate all the properties of the system, right? So how can I imagine calculating all the different probabilities and all the different eigenvalues or values of the energy or the magnetization or whatever observable do I have if everything is complex and complicated? So the idea of statistical mechanics, as I told you, is to start from something very simple and build this up. So instead of trying to solve everything all together, statistical mechanics says, well, let's start with simple models where we know something about the energies, where we know something about the probabilities, and try to build a formalism based on those very simple assumptions. And little by little, we will complicate our assumptions, and maybe something good will grow out of it. Okay? Now, why this idea is actually makes sense? Because this is also the blessing of systems with a lot of particles. At some point, like the central Gaussian limit theorem, you don't really care about a lot of stuff. You only care about very small number of parameters, and that's it. The same goes over here. So yes, the statistics is going to be very complicated. But in the thermodynamical limit, where we have 10 to the power 22 particles, 23 particles, okay, it won't matter. A lot of different small details won't matter at all. Okay, so this is the prescription. Now, what is the simplest probability that we have been taught in first class, first year of undergrad studies? Right? Uniform, right? So the simplest assumption is, why won't we start with uniform probabilities, okay? And moreover, we will also say that the energy is constant. So we have, let's write it down. Simplest assumptions. Okay. E, the energy of the system. Is constant. And all the states have exactly the same energy. Okay. So what I mean by constant, any state is have exactly the same energy. It's not modified when the system goes from one state to another, right? This is the first assumption. The second assumption, so if you remember, E average is a sum of I, Pi, Ei. Okay? So we made our assumption about this part. What are the different energies of the system? Okay? Now we need to tell us or assume something about the different probabilities of the different states. Okay? So this is assumption number one, simplest assumption. All of those are constant. Assumption number two is that probability is uniform. Meaning for all I, Pi equals to the same C. Okay. Those two assumptions form, you cannot assume something even simpler than that. General and still simple. Okay, the uniform probability is the simplest assumption in probability theory about probabilities. Constant energy is also the simplest case, right? Anything else where the energies are different for different states is a complication of this first assumption. So this is called micro-canonical ensemble. Right. So we want to compute averages. We want to compute ensemble averages, and we, instead of saying, well, we will take a regular system and we will try to see what's going inside, instead we're saying, let's assume something about an imaginary system, a model system, right, where we know something about the energies, where we know something about the probabilities, and let's see what happens. All right, so this is very nice. But what exactly can we do now, right? I'm telling you, great, we have those two assumptions, but eventually I want to go and measure stuff and want to predict something about the system, all right? How can I do this? I need to establish a connection between those assumptions that work for microstates. So, and the energies of those microstates and the probabilities of those microstates and some global properties. What are the global properties? Something that you can use in thermodynamics, right? Average energy of the system, average, something about the entropy, something about the temperature. Okay? Those are the regular quantities that people use in the lab. Okay? So nobody really goes and calculates the probabilities or the different energies. Maybe today we already are, but the general approach, no, you average, you have a macroscopical system, you don't know a lot about the microstates, you want to calculate something which is macroscopical. What is the connection between those microscopical descriptions and macroscopical descriptions? And the idea is actually really nice. Remember entropy? Yeah, we have entropy, but we have no idea what entropy is. Now, the idea to make a connection between microscopical world and macroscopical world is by definition of the entropy. We will define entropy, and we will use entropy in order to establish a connection between thermodynamics and very simple assumptions of statistical mechanics. Now, here it's an assumption what entropy is. We know that there are some constraints about entropy. Okay? So entropy have to be a function which grows with energy. Entropy should have maximal value when the energy is kept constant in equilibrium. Okay? So based on those constraints, and those basically are the only two constraints, based on those two constraints we can construct our entropy. Okay. Now, we don't have a lot in this ensemble. It's a very simplistic ensemble. Because all the energies are exactly the same, but there are different states. Right? We can go over all those different states. Now, let's think about the second property, that the entropy is maximal, right? At equilibrium. So you set energy, okay? You set energy, and then you know that in equilibrium the entropy has to attain a maximal value. Now, there is also something else that attains a maximal value for this example, and this is number of states. So let's assume that I keep my system simple, I keep the energy constant, and then I start to introduce constraints to the system, right? So if you think about it, this is my system, okay? And I start to introduce constraints, meaning I, for example, do not allow the particles to cross this blue line. So as I increase this blue line, the number of states inside the system, or the number of positions that the different particles can occupy inside my box, so the red dots are my particles. So as this blue line grows and grows and grows, the number of states that those red particles can occupy should go down, right? So I can associate the maximal number of states with constraint. Okay, so the number of the number of states is maximal with respect to constraints. When I add any constraint to the system, the number of states goes down. Right? So there is something about maximality, maximum value of the number of states, and we also know that there is something about the maximal entropy. Okay? And here comes the assumption. The assumption says, well, let's say that the entropy is just the number of states of the system. Okay? Should work fine, right? So we don't really know what the entropy is. We don't, number of states, well, we understand what number of states is. Let's associate them together. Okay, so can we say that S equals to the number of states? What do you think? Is it a reasonable assumption? Do we break something if we assume this? I haven't told you or reminded you that, well, I told you about two things about entropy. Growth with energy has a maximal value, but there is a third condition. What is the third condition? No. Close enough. Extensivity. Right? Entropy is an extensive function. Okay, so it's not just enough to say, well, this guy has a maximal value, this guy also has a maximal value. Let's associate them together. Okay? When we associate two quantities, the extensivity property should be the same on the right-hand side and on the left-hand side. Now, is the number of states is a linear property or it's a multiplicative property? Okay. What do you think? So if I have a dice, okay? How many states the dice have? I roll it. Six states, right? Number of states is 6. Okay? I have another dice. The number of states of the second dice is 6. But if I have 2 dice, okay? What is the number of states for a system which is the outcome of a roll when I'm rolling 2 dice? 36. So the number of states is not an extensive property. It's a multiplicative property. Right? As long as all the different stuff is independent. If it's dependent, well, it's already a little bit more complicated. But the number of states, it's not extensive. So we cannot simply associate the number of states of the system with the entropy. But we can do something, right? If it's multiplicative, the number of states. Okay. If the number of states is a multiplicative property, we can convert this multiplicative property into an extensive property. How we can convert it? A logarithm, right? So we can say the following. No, S is not exactly the number of states, right? But we can write down that S is a logarithm of the number of states. Okay? But this is just a number, and entropy has some sort of units. So we can plug over here constants that will take care of the units of the entropy. Okay. So basically, this guy is extensive. This guy is also extensive. This is going to have a maximum on some specific point. This is going to have the same maximum. Okay? So we can define our entropy, which is now based on microscopic properties, the number of states, and say, well, all the time, at least for this ensemble, all the time that we spoke about different entropies and what entropy does and what entropy does not do, it was always like that. Okay? You don't have to assume, well, it's just some general function. Now we have a prescription or assumption, okay, that the entropy is actually k Boltzmann and it's a logarithm of the number of states. Okay. Yes?
למה כשאני מכניס את הלוגריתם אז זה הופך את זה כן אקסטנסיבי?
So if you have 3 multiplied by 5, log of 3 multiplied by 5 is log of 3 plus log of 5. Right? That's it. So if you had two systems, the number of states of two systems is a multiplication of the number of states of system A and the multiplication of the number of states of system B. Right? But the entropy is, has to be extensive. So if you take a log, it's a log of the number of states of system A plus a log of the number of states of system B. So the entropies are extensive. Yes? Yes, two questions.
אחד, מה המוטיבציה שלנו? כאילו, מה הייתה המוטיבציה שלנו להגיד שהאנטרופיה קשורה איכשהו לכמות המצבים?
The maximal principle. So the first question is, what is our motivation to define or associate the entropy with the number of states? So this is the principle that entropy attains a maximal value. And the number of states also attains a maximal value with respect of introduction of constraints. Right? The same goes, so you introduce constraint to the system, the number of states goes down. Now you take an entropy, it's an equilibrium. How you put the system a little bit outside the equilibrium, you push it outside of the equilibrium, you can introduce a constraint, you can build a wall, and the system will get out of this equilibrium and the entropy will go down. So both quantities are going down when you introduce constraints into the system. אילוץ. Constraint, it's אילוץ in Hebrew.
שאלה שנייה, היסטורית. קודם כל,
No, nobody did it like that. It was developed on Boltzmann gas theory and a lot of interactions and particles that are hitting each other and Gibbs assumption, etc., etc., etc. It's a short story, how we understand it today. The original development was different. Yes. Yes.
Where did Boltzmann constant come from?
Units. Units. That's it.
Okay, that's it.
That's it. That's just units. Yes. So try to build, you have an equilibrium and then you prevent the system of going into some specific states. It means that equilibrium have to be different. So for example, so this is my box, okay? And those are my particles. And they spread everywhere around it, okay? Great. Now, I'm introducing a constraint into the system. How am I introducing a constraint into the system? I push some of the blue particles away, such that they cannot cross this border. This is introduction of a constraint, okay? So now all the blue particles are over here. Great. Okay. Now comes the trick. If I will erase this constraint, the system will adiabatically go from this state to that state, right? Okay. What happens if a system goes adiabatically from state A to state B? The entropy grows. Okay, so the entropy at this state is lower than the entropy of the original state, meaning introduction of constraints lowers the entropy. The same goes for the number of states. So if you introduce a constraint, it means some of the states cannot be occupied. And if they cannot be occupied, the number of states goes down. Okay. Now this again, ideology, we define it like that. We can wave our hands around it, and this is what people did originally. We don't have to do it anymore. Yes?
The number of states, for example, in our ensemble is, I don't know how to really think about it because
you need an example. I will come to an example and you will understand it a little bit better.
Yes, but for example, if we have the dice,
yes,
we have states that are the same. We do have 36 states, but some of those states are the same. How do we go about saying that those states are the same? Does it matter? I mean, if we look at...
If they are the same, if I say that all the energy is exactly the same for all the states, they are the same.
Yeah,
does it matter that they are the same?
I mean, I can say, for example, in our ensemble that I have infinite number of states that all have the same...
It's going to be your ensemble, not mine. In my state, there are some specific number of states. For each energy, there is going to be a specific number of states. It's not going to be infinite, right? Because the universe is limited as far as we know. Okay, so eventually you have a hard limit. Okay. Any other questions? Yes.
Can you explain again why the number of states is increasing function of the energy? If I increase the energy, why does the number of states have to grow?
So it depends on how you this is a tricky question. Okay, so it's actually you see this in examples. Okay, so it's a general assumption, and we need somehow to verify it for each example and example. But you will see that the number of states for any example that we use is going to be a growing number of the energy. Okay. Other questions? No. Great, so we have this, and now we have a prescription, okay? Why we have a prescription? Because, well, the moment that we have entropy, there is a very simple transformation from entropy to temperature, right? 1 over T equals to ds du. Right. So if we have our energy, U is our energy, and we somehow we manage to calculate the entropy, we will derive this entropy with respect to the energy of the system, we will get a connection to the temperature, and that's it. This is our established link from microscopic behavior to macroscopic behavior in terms of energies and temperature. Okay. So idea, again, for microcanonical ensemble. First, we calculate the number of states. Let me write it down. The prescription is very simple. 1. Define the model. 2. For fixed energy, calculate the number of states. Let's call it omega of E. 3. Calculate the entropy. S equals K Boltzmann log of omega E. Number 4, compute the temperature. One over T equals ds over dE. That's it. That's the whole story of microcanonical ensemble. Eventually, we will have an equation which we can go and test, compare it to experimental data, etc., 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 etc. We start with simplistic model, microscopical model. We go all the way to macroscopical behavior. Right? Great. Yes.
למה אנחנו צריכים את השלב הראשון? הרי כאילו, איפה השתמשנו בזה שנגיד הגדרנו
So all of this works for specific models. Statistical mechanics is not something that you say, well, we have a general behavior or general prescription. This is a general prescription, but it has to be has to work on top of something. We need a specific model to work with, always. Right? So in statistical mechanics, you always have to keep in mind, simple example for which you're doing something. Right? The idea is not that I have a very general behavior. Instead of, I have simple models that describe to me everything else. So it's the opposite of thermodynamics. In thermodynamics, I want a very general equations of states, where I don't really understand all the different components. I maybe have a feeling about them, but I don't really understand them. Statistical mechanics is the opposite. You define simple model, you use assumptions, like this microcanonical assumptions, and then you derive a general equation, right? But they always start with a specific model, okay? Let's see an example. Two-state model. Okay. So what is this two-state model? We have n particles. The number of particles. Each particle the energetic spectrum is very easy. It can have either energy 0 or energy epsilon. Energy of each particle. Okay. So we're working on n different particles. Each of them have two energetic levels, 0 or epsilon, okay? And we assume that the particles do not interact, okay? Which is important. Okay. So this is number one. This is the definition of the model that we want to work with. We want to obtain some equation of state of this model. We can want to make predictions based on this simple model, etc., 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 under the assumption of microcanonical ensemble. Okay, so this is state 1, or we're done with this. Stage 2, this is 1. 2, for fixed energy E, calculate the number of states omega E. A lot of space. E, the energy of the system. Okay. Now, what do we know if the energy of the system is exactly E? What do we know?
There is an integer that times epsilon equal to E.
Exactly. So we know that E divided by epsilon, number of particles in excited state. Okay, so each particle has a ground state and an excited state, and if I know for sure that the energy of the system is E, then E divided by epsilon is exactly the number of star particles that are sitting at excited state. Okay, now I need to calculate the number of states. So what are the different states? The different states are the different particles, so different configuration of the different particles, where some of them are in excited state and some of them in the ground state. I can switch between different particles, right? And those switching between different particles, particle A is going to be in state epsilon, in excited states. Particle B is going to be in the ground state. Can be state 1. Particle A is in a ground state. Particle B in excited states, it's going to be state number 2, etc., etc., etc. So I need to count all the different configurations. Okay? So it's a combinatorial question, right? It's a combinatorial question. So the question of different states is the question of picking up E divided by epsilon out of how many particles? N. Okay, so pick E divided by epsilon out of N with, we don't care, do not care about the order. So we know that the number of states is the number of ways to pick up E divided by epsilon out of N, and this is just N above E epsilon, or how the students call it, choose function. Okay? Which is N factorial divided by E by epsilon factorial, and N minus E divided by epsilon factorial. Okay, so this was number 2. Was number 2. Number 3. Number 3. Calculate the entropy. Calculate the entropy. S equals to K Boltzmann log of omega. Okay, so this is K Boltzmann log of whatever stands over here, which is N factorial E by epsilon factorial N minus E divided by epsilon factorial. Great. It's actually not so great. Why? Because in a second we will need to take a derivative out of this entropy with respect to E, right? So we will need to calculate something like ds to dE, which is a derivative of some factorials over here. Okay, so the derivative factorial, it's a nasty thing. So instead of leaving all of those factorials over here, we are going to use Stirling approximation for all the factorials that we have inside. General question, when Stirling approximation works? Wrong. Works, so, right, so what is log of n factorial? It's approximately n log n minus n, and there is something, log of square root of 2 pi, etc., etc., etc. So usually we are taught that this approximation, this is Stirling's approximation. Usually we are taught that it works for very large numbers, but it's not true. It works for really pretty small numbers like 10. Okay? So we don't, and in our systems, n is a large number, so it for sure works. But even if n is not so big, it will still work if you take this additional square root of 2 pi over here. Anyhow, we want to take the derivative of the entropy with respect to energy. We don't like factorials. We're going to use Stirling approximation in order to calculate this expression over here. Okay, so some algebra on the way. So what we have over here, we have S equals to K Boltzmann log of n factorial minus K Boltzmann log of E divided by epsilon factorial minus K Boltzmann log of n minus E divided by epsilon factorial. Okay. Let's keep K Boltzmann out. Okay, so we can say that it's K Boltzmann multiplied, and now we're using Stirling approximation for all of those logarithms. So here we have n log n minus n. This is this guy. Second guy is minus E divided by epsilon log of E divided by epsilon plus E divided by epsilon. Okay, so I apply this formula to this logarithm. Next thing is minus n minus E divided by epsilon log of n minus E divided by epsilon plus n minus E divided by epsilon, and that's it. Okay. And we have those parentheses over here. Okay. Now let's try and work out what exactly we have over here. So put it over here. So I have this term, and I have also here some n and some n. So what I'm going to do, I'm going to expand this logarithm of n minus E epsilon. Okay. So I'm going to say that logarithm of n minus E epsilon, it is logarithm of n1 minus E divided by n epsilon, and it is logarithm of n plus logarithm of 1 minus E n epsilon. Right. Now I'm going to substitute it inside this nasty expression. So what do we have? So S equals to K Boltzmann, and we have n log n minus n minus E divided by epsilon log of E divided by epsilon plus E divided by epsilon. Okay, so those are these terms, this guy and that guy. Now, since I separated this logarithm into multiplication of two, or summation of two logarithms, you see I have here minus n log of n. Okay, so we're going to have minus n log of n. Okay, so this is from multiplication of this guy by the first other part. Also, we have plus n logarithm of 1 minus E divided by n epsilon. Right? And also we have minus E divided by epsilon logarithm of n plus, and here it's a minus, right? And here it's a minus. And also we are going to have plus of E divided by epsilon logarithm of 1 minus E divided by n epsilon. Those are parentheses.
Plus n minus e
Yes. Plus n minus e divided by epsilon. Great. Fun part. This guy goes with that guy. This guy goes with this guy. This guy goes with that guy. This guy goes with... Where is this? Should be something. Oh, I made a mistake. Okay. This guy doesn't go anywhere, right? This guy doesn't go anywhere. Okay. So we have this part and we have this part, right? Now, where this part came from, I made a little mistake on the way. Hello. This guy was plus e divided by epsilon log of n minus e divided by epsilon. Okay. Now, I need to cancel. I have this prefactor, which is e divided by epsilon, and I want to take out of this logarithm, instead of taking n out of this logarithm, I'm going to take e divided by epsilon out of this logarithm. So this term I will write down as e divided by epsilon multiplied by log of e divided by epsilon, and here I'm going to have n epsilon divided by e minus 1. Okay, and it equals to e divided by epsilon log of e divided by epsilon plus log of n epsilon divided by e minus 1. Why I did this? Because I have this term over here, which is e divided by epsilon. Now, out of this term, I have also, with a minus sign over here, here I have a plus sign, e divided by epsilon log of e divided by epsilon. Okay, so this guy goes with that guy. Okay. Now let's sum up what we have so far out of this big mess. Certain approximations are always messy. Okay, so we have the following. So S equals to K Boltzmann minus n logarithm of 1 minus e divided by n epsilon. This is this term. Plus e divided by epsilon logarithm of n epsilon divided by e minus 1. So now it's not so bad, right? We have n, we have log. It's much nicer equation than what we had in the first place. Okay. What we are doing now, so we have entropy. We got rid of all those factorials that we have. Now we can take this equation and we can use it in order to find what is our entropies. Right? Now we haven't missed anything, right? Yes. Or we did miss something. Everything should be fine. Everything should be kosher. All right. Next thing is, this is already 4. So this is 4 is 1 over temperature equals to ds to dE. Alright, so another game starts. We know what is 1 over t. We need to calculate this derivative of the nasty thing that we have over here. So ds to dE equals to d to dE of k Boltzmann minus n log of 1 minus e divided by n epsilon plus e divided by epsilon log of n epsilon divided by e minus 1. So we don't care about k Boltzmann. We only care about expressions where e appears. And the derivatives are pretty simple. So what we have here are logarithms and some polynomials. It's pretty simple. So we get k equals 2. K Boltzmann is outside. Let's take a derivative with respect to this guy. Okay. So this is minus n divided by whatever stands in the logarithm, which is 1 minus e divided by n epsilon, multiplied by whatever the derivative of whatever stands inside the logarithm with respect to e, which is minus 1 over n epsilon. Okay. Now we take the derivative of this guy. So first of all, we have the derivative with respect to e. So this is plus 1 over epsilon log of n epsilon divided by e minus 1. Right. Plus e divided by epsilon. The derivative of the logarithm is 1 over n epsilon divided by e minus 1. And the derivative of this guy with respect to e, it is minus n epsilon divided by e squared. Close all the parentheses, and this is what we have. Okay, let's see what we have. So some additional massaging is needed. So first of all, we see that there is some sort of a logarithm over here. And there are no logarithms for this expression and that expression. So let's try and make something out of those two. Okay, so we keep k Boltzmann on the outside. And we try to do the following thing. So first of all, we multiply this by n epsilon. And what we obtain is this is n divided by n epsilon minus e. Right. We keep this term as it is, 1 over epsilon log of n epsilon divided by e minus 1. And we need to do something with this term over here. So let's see what we do. We multiply it by energy. E, so E and E is going down. This guy goes with that guy. And this guy, okay, so what we're left with minus n divided by n epsilon minus e. Okay, this is really very nice. Favorite part. This guy cancels out. Okay. And what we obtain is this is k Boltzmann 1 over epsilon log of n epsilon divided by e minus 1. So we started with the long equation, we made it even longer, and after a while, after taking this derivative, it's actually becoming quite nice. Right? So, because at the end, what we have is as follows. One over t equals to k Boltzmann divided by epsilon log of n epsilon divided by e minus 1. Okay, so we have epsilon divided by k Boltzmann t equals to log of n epsilon divided by e minus 1. First of all, let's check the units. Energy, k Boltzmann t is also energy, joules. N is unitless number, so units of energy divided by units of energy. Everything is fine. At least, and this is always the first thing that you need to do after you work a while with a lot of algebra, is to see whether the units are okay. Great. Now, we can solve this. We can solve this. And what we do, so let's take an exponent of the left-hand side and the exponent of the right-hand side. And we're getting that e to the power epsilon divided by k Boltzmann t equals to n epsilon divided by e minus 1. All right. The next thing is e epsilon k Boltzmann t plus 1 equals to n epsilon divided by e. Or e equals to n multiplied by epsilon divided by 1 plus e to the power epsilon divided by k Boltzmann t. Hooray, hooray! This is our equation. We found how the general energy of the system is related to the microscopical quantity, which is the energy of the excited state, and the temperature of the system. Okay. So we started with a model. We used assumptions about distribution of the energies, distribution of the probabilities, etc., etc., etc. We use this connection, and this is what you always use when you assume microcanonical ensemble. You always use this connection between number of states and entropy. You calculated the entropy. You made a lot of mess with all this algebra. It took us something like 15 minutes or so. But eventually, in most of the cases, you obtain something very, very nice. Okay? So, first of all, is this extensive? Is this result? So, is it extensive? The first thing that you check, you get an energy. Yes, it's extensive. Why? Because there is no volume. The size of the system over here is just the number of particles. They do not interact. They don't see each other. So now I will make my system twice as big. What do I mean by twice as big? I just include 2 n's instead of n. The only thing that I will get is just by a factor of 2 over here. That's it. So the system, so the energy is, it is extensive. Our assumption is kept fine. It's proportional to energy because the units of epsilon, this is the energy of a single state, or of the excited state. The units are also fine. And what we will see that those prefactors like 1 plus exponent of some energy divided by k Boltzmann t, it's always there. Yes? The question is, where we assume that the probability of all the energies is exactly the same. In the microcanonical ensemble. It's rooted over there. When you compute the number of states and you say this is the entropy, etc., 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 over there you used the assumptions that the probabilities of all the states are exactly the same. It is rooted in the assumptions of microcanonical ensemble. It's there. Okay, now what can we do with this guy? We can calculate something that an experimentalist or anybody can go and measure. Okay? So what usually experimentalists measure in condensed matter when you have some kind of matter? So heat capacity, right? So heat capacity, C dE to dt. How the heat capacity, okay, and then I can plot the heat capacity with respect to temperature. And the measurement is quite simple. So you heat up the system and you can measure how much heat you have to invest in order to bring the temperature of your system from T1 to T2. By doing this over and over again for different temperatures, you can obtain the heat capacity with respect to the temperature. Okay? And this is something that is routinely done in many systems. Okay? How exactly this guy is going to behave for our simple system. Okay? So we have to take this guy and take another derivative. Okay? Okay, so C equals dE to dt, it equals to d to dt of n epsilon 1 over epsilon e k Boltzmann t. You don't care about the prefactors, they out, and epsilon d to dt of 1 over 1 plus e to the power epsilon by k Boltzmann t. Okay, so this derivative is n epsilon. And here what we are having is minus 1 divided by 1 plus e epsilon by k Boltzmann t squared multiplied by e epsilon divided by k Boltzmann t. So the derivative of this guy with respect to the temperature is just the exponent, and the derivative of the exponent, or whatever stands inside the exponent, is minus epsilon k Boltzmann t squared. Okay, so let's try and get rid out of everything which is what is not necessary. So it equals to n epsilon squared e epsilon by k Boltzmann t divided by k Boltzmann t squared. Okay, and here we have 1 over e to the power epsilon by k Boltzmann t squared. Okay.
What exactly is C again?
What is T?
What is C?
Heat capacity.
Okay.
Right? This is heat capacity. We studied this in the class of thermodynamics. How much heat you have to invest inside the system, how much energy in order to raise its temperature. So when we plot this, we'll get that the heat capacity raises up and then it goes down. Okay. This is the feature of two-level system. So what happens, and it has this very nice name called, have you heard about semiconductors, development of semiconductors, etc., etc.? So there is Schottky, which is always involved with something, with everything that's related to semiconductors. So this is called a Schottky hump. Okay. What happens physically? And it can be observed in many systems, in any two-level systems. All right. Moreover, in many semiconductors, specifically this property is extensively used. Now what happens, right? So let's try and understand. We got a curve, right? There is a bell shape. It's not a Gaussian, it's something else. Okay? What's the meaning of this thing? Okay. Now let's go to very low temperatures. So for the very low temperatures, we can look on the energy, okay? We can look on the energy and we say, well, if the temperature is extremely low, so T going to 0, it is an exponent of 1 over T, so it's an exponent of a huge number. So we have a very huge number over here, right? So the energy of the system, it's going where? To 0. So for low temperatures, the energy of the system is going to 0. Now, remember, the energy of the system is the number of particles that are sitting in an excited states. Okay, so for very low temperatures, if the energy is almost 0, it means that almost all the particles are sitting in their ground states. Okay? Great. This is the description. You raise your temperature. The energy will go up a little bit. This is why the heat capacity is going up. Okay, so you raise your temperature, the energy is going up. Why it's going up? Because more and more particles can occupy the excited state. Okay? So you raise your temperature and more particles are occupying the excited state. You raise your temperature a little bit more and there are more particles that can occupy the excited state. Now there is plenty of room over there. Why there is plenty of room over there? Because at low temperatures almost nobody really occupying the excited state. Right? So you're raising your temperature, more particles are getting to the excited state, the heat capacity goes up and it goes up and up and up. Works great. But at some point, what we see over here is that it starts to go down. Why it's going down? Why I cannot use this argument that I'm raising my temperature and I have more particles that are occupying, and I raise my temperature again and more particles are occupying the excited states. Why this phenomena suddenly is stopped and the other way is observed? Yes? Great. So the answer is, at some point, almost all of the particles are sitting in their excited states, and I'm raising my temperature, and the system cannot bring any other particles from the outside. So nobody is occupying new states. The energy is saturated. Its derivative is going towards 0. Okay? So what we are having here is we have a lot of states, particles are occupying those states. At some point, almost all the states are occupied. Nobody can occupy in other states. And then the heat capacity goes down. Now, this is nice. Why it's nice? And it's related to the electronic bands in semiconductors that the particle can have. You can see either at a ground state band or an excited band. Now, what will happen if I'll say, well, I measured my system, and this is what I have seen. You can say, oh, great, my system, somewhere inside my system, sits at two-level behavior. I have a lot of particles, they are doing something with each other. I don't really know what exactly they are doing, but by measuring this heat capacity, I can understand a general behavior of my system. There are two-level systems inside. Maybe they are not talking, maybe it's not exactly simple particles, maybe this is something else, but there is a two-level behavior. Okay? So it's a predictive tool. And it's used in semiconductors. But what if I will say the following? Yes?
לפי הסדר שלנו, אבל כאילו למה בהתחלה השיפוע הוא קטן? כאילו השיפוע צריך להיות, ככל שאני יותר קרוב לאפס, השיפוע צריך להיות יותר גדול.
It's going to be exactly defined by this guy. Okay? So I'm not saying that the experiment fits exactly what happened. So is the slope exactly fits? So the only thing I can say is that the slope is growing. That's it. How exactly? We will. There is a problem with this behavior, and we will come to that. Okay. So what I want to do is, let's assume that I'm an experimentalist. I took a material, I measured its heat capacity as a function of temperature, okay, and I got this Schottky hump. And I'm extremely happy because I know that I have a two-level system at some state. Now, I would say, well, but why stop over here? I have a lot of, my machinery can produce a lot of heat. I can raise my temperature even more. So what will happen if I will heat up and suddenly I will start to see another hump? What happens?
Another level?
Another level. Okay. So think about it. I can heat up my system. Okay. I can heat up my system, and I can look on the behavior of the heat capacity, and I know that any peak for this heat capacity means that I have two levels. Another peak, what it means. So why I said to you that the heat capacity is going down? Because all the states are populated. Okay. Another peak means that I inserted a lot of energy into the system such that the system said, well, actually, Stas, we haven't told you all the truths. Somewhere over here, if this is 0, this is epsilon 1. And you inserted enough heat into the system such that the particles that were sitting in the first excited state discover that they can jump to the second excited state. And this you can see by observation of additional peaks for the heat capacity. Now, as you mentioned, and as I told you, this is a very oversimplified model. Okay? The energies are different, etc., etc., etc. So the exact behavior at low temperatures won't fit the experiment. Okay? If it's going at what rate the heat capacity is going up. It will always go up, but exactly how fast or how slow, it actually depends on the details of the model. And we will see that we have to modify our model in order to fit it to real-life experiments. But the fact stays the same. The behavior, qualitative behavior of the heat capacity for two-level system, any two-level system, is actually pretty well described by this equation over here. Okay, so there are other examples of microcanonical behavior. You will see another example with your TA. The problem with microcanonical ensemble is twofold. First, it's too simple. We know for sure that there are systems with different energies for different states, and this assumption is that all the states are equally probable and all the states have exactly the same energy. It's simply not true. Okay? So this problem number one. Problem number two is it's very simple to describe the microcanonical ensemble, but it's actually hard to solve almost anything. Why? Because there is this component at stage number two. Computation of the number of states. So I waved my hands over here, and this is actually a simple system, and I said, well, the number of states was n factorial divided by e by epsilon factorial, and here I have n minus e by epsilon factorial. I mean, it's a simple system, and you actually need to choose something. It's actually simple, but the more complex my system is, the more particles are there, the more constraints I introduce into the system. This part of computation of the number of states, but because it's a combinatorial problem, it's becoming an awful part. So we are capable of computing it for simple systems, right? But the more complex the system is, right, this task is unbearable, really, really unbearable. So we have two problems with microcanonical ensemble. A, it doesn't really describe nature because nature is not equally probable states. B, it seems easy, but it's not. Okay. Now, for our purposes, we're using it to describe the idea of building an ensemble, but for anything else, we are going to use this microcanonical ensemble in order to develop more general, more complex, and more realistic behaviors like canonical ensemble, grand canonical ensemble, and etc., etc., etc. So we're pretty done with the microcanonical ensemble, and next week we will start canonical and grand canonical not yet, but canonical ensemble. See you next week. Hi. פתרון כל בעיה. כל בעיה.
עוד דבר.
כן.
בהתחלה,
ההיפותזה הארגונית? כן, מה, לא הבנתי. אנחנו מניחים את זה.
מניחים את זה שבכל מערכת?
אנחנו מניחים עד שזה לא קורה, ויש מערכות שזה לא קורה בהן.
אוקיי, תודה.
כן.
יש לי שאלה, אני מסתכל על הביטוי של הטמפרטורה, ונגיד לוקח את הטמפרטורה לאינסוף. כן. אז אני מקבל שרק חצי מהחלקיקים, כאילו יש במכנה 2.
אז כי, אני אסביר לך, כי כבר לא אכפת לך מה האנרגיה. האנרגיה הקינטית שלך, תחשוב על זה בצורה כזאת, הטמפרטורה זה סוג של אנרגיה קינטית. האפס והאפסילון זה אנרגיה פוטנציאלית שלך. אוקיי? עכשיו, ברגע שהטמפרטורה שלך גבוהה, אתה לא מרגיש את ההבדל בין אפס והאפסילון, בכלל. לא מרגיש בכלל. ואתה בכל מקום, ולכן זה טבע.
זה כאילו להיות באפס ולהיות באפסילון זה אותו דבר.
בגלל הטמפרטורה זה ביטוי לאנרגיה קינטית, האנרגיה הזאת זה אנרגיה פוטנציאלית, ובאיזשהו שלב היא לא משנה. כן.
אני לא הבנתי איך זה, הבנתי שהשאלה להיות בכל מצב, אבל כשאתה לא השקיע, ככה או ככה, זה לא השקיע.
אני אסביר לך, בואי נגיד שיש מצבים עם הסתברויות שונים, אוקיי? אז ברגע שאני מכניס כל מיני אילוצים, אני לא בהכרח אקטין את האנטרופיה. או אני לא, כי המערכת אולי לא תושפע מזה שאני מכניס כל מיני אילוצים. כי אם יש לי הסתברות, או מצבים עם הסתברויות גבוהות מאוד, ואני לא משפיע על המצבים האלה בהכנסת האילוצים, אז המערכת כמעט לא תרגיש את זה.
מה הכוונה? אני נגיד שתפרנו את המצבים, נגיד חלקיקים ככה וככה, זה לא היה משהו...
תחשבי על זה ככה, הקובייה שלי כל הזמן מראה 6. ואני הכנסתי אילוץ, כל הזמן היא מראה 6. ואני הכנסתי אילוץ כזה ש5 אף פעם לא יוצא. זה משפיע על משהו? אם היא בכל מקרה כל הזמן מראה 6. אז היא לא משפיעה.
אז אבל כבר אתה עשית אילוץ שזה משפיע.
סבבה, בואי נעשה את זה. התוצאה ל6 זה 1 מינוס אפסילון קטן, ו5 זה משהו ממש קטן, או זה לא משנה. עכשיו, היא בכל מקרה עדיין, יש הסתברות לזה שהיא תראה 5. אוקיי? הכנסתי אילוץ, אבל זה עדיין כמעט לא שינה כלום, כי ההסתברות ל5 הייתה ממש קטנה.
אפשר גם בדוגמה הזו
המצבים...
מה?
נניח יש לי מצב שהכנסתי אנרגיה ככה שזה כבר לא במצב היסוד, ואז אני מכניס את האילוץ שהיא לא יכולה להיות במצב היסוד, אז זה לא ישנה.
ברגע שיש לי הסתברויות שונות, קודם כל, אני לא יכול לעשות את ההשוואה הזאת, בדיוק למה? בין האנטרופיה לבין מספר המצבים. ואז את אולי יותר תביני. והרעיון הוא זה שברגע שיש לי מצבים שהם לא שווים הסתברותית, השינויים של אילוצים משפיעים בצורה שונה, תלוי איך אני הכנסתי אותם. אז האילוצים האלה הם לא בהכרח יקטינו את האנטרופיה שלי, ולכן האסוציאציה הזאת לא עובדת. זה בעצם, הבעיה תלויה באיך אני מגדיר את האנטרופיה שלי. משם זה מגיע.
זאת אומרת, ברגע שאנחנו לא מחליטים על הסתברות אחידה, אז אנחנו כבר לא יכולים
אנחנו נגיע להגדרה הבאה, שהאנטרופיה תהיה מינוס K בולצמן, סכום על כל המצבים, PJ log PJ. נגיע לצורה הכי כללית של האנטרופיה, שנראית ככה. אז היא תלויה בהסתברויות. רק במקרה שיש לי הסתברויות שוות, אנחנו נקבל ש-S שווה ל-K בולצמן לוג מספר המצבים. רק המקרה הספציפי הזה. אנחנו נבין למה זה. לא נבין, אנחנו באיזשהו שלב נגיד, בוא ניקח את זה כהגדרה, ומשם נזרום.
אוקיי.
בסדר?
אפשר עוד שאלה?
כן.
אני חושבת שזה אולי קשור למשהו יותר בסיסי, כאילו, כשאנחנו אומרים משיווי משקל לשיווי, כאילו נגיד היה, אנחנו כל הזמן, נגיד, תיארת היום את המצב שאנחנו עושים את הסוגרים את הזה, והם לא מאפשרים להגיע. אז גם במצב החדש אנחנו בשיווי משקל, נכון, כי היה אילוץ, אבל שיווי משקל חדש של האילוץ.
נכון. האילוצים, בדרך כלל, הכנסה של אילוצים נוספים, תמיד תזיז לי את המערכת לאן שהוא, אבל ברגע שאני אוציא את זה, בגלל שהמערכת הייתה כבר לפני זה בשיווי משקל, היא תמיד תחזור לשם. אז אם המערכת חוזרת בעצמה לאיזשהו מצב, זה מחייב את האנטרופיה של אותו המצב להיות יותר יקר.
כן, אז מה, באופן כללי, אבל גם המצב החדש הוא שיווי משקל של משהו.
אין שום בעיה, זה בסדר, זה בסדר.
אז מה המקסימום בו? כאילו, איזה מקסימום?
בעזרת אילוצים נוספים, עוד אילוצים שאני יכול להכניס את המערכת, זה תמיד. אני הגדרתי את המערכת, אז אמרתי, בסדר, זאת המערכת שלי, ככה היא חיה. הכנסה של כל אילוץ חדש, אוקיי? את צודקת, זה יכול ליצור מצב שיווי משקל חדש, נכון. אני מוציא את האילוץ, חוזרת למצב שיווי משקל ישן. זה אומר שהאנטרופיה של מצב שיווי משקל ישן יותר גדולה מהאנטרופיה של מצב...
זאת אומרת, נגיד שהיה לנו את האילוץ, אז אנחנו עוד פעם הגענו לאנטרופיה המקסימלית שיכולה...
בהינתן אותו אילוץ, כן.
סבבה, תודה רבה.
בבקשה. כן.
שתי שאלות. אחת זה פחות או יותר המשך של השאלות שלנו, אני פשוט מאוד הסתובבתי כי אמרת שאנטרופיה שואפת למקסימום בשיווי משקל, מספר מצבים דווקא אפס, הוא שואף לכמה שפחות מצבים בשיווי משקל.
לא, למה?
למה? כי בשיווי משקל אתה מגיע רק למצב אחד בעיקרון.
לא. אתה ספציפית במיקרו קנוני, זה מצבי שווה אנרגיה. האנרגיה שלי קבועה, יש לי טונות של מצבים. זה מצבי שווה אנרגיה, אין לי מצב אחד. אוקיי, הסתכל, שני חלקיקים, כן? אחד למעלה, השני למטה. שני מצבים, כאילו כשאני אחליף אותם, כן? זה יהיה למטה וזה יהיה למעלה. זה שני מצבים שונים של המערכת. זה לא שהמערכת תגיע והיא תשב רק פה. היא יכולה להיות גם פה, היא יכולה להיות גם פה. שני מצבים, בסדר?
הבנתי. אבל פשוט כאילו, עם הדוגמה שנתת עם הקובייה שאתה דוחף, זה בעיקרון היית בשיווי משקל ואתה מפר?
אני יצרתי משהו אחר. אוקיי? והמטרה היא שעכשיו נניח אני אוציא את האילוץ, מה יקרה למערכת? תחזור לשיווי משקל המקורי, ולכן האנטרופיה חייבת לעלות.
כשהוספת אבל את האילוץ, המספר מצבים ירד.
נכון. וגם האנטרופיה ירדה. אתה רואה? מתנהגים ביחד.
הבנתי.
אבל בסוף אנחנו נגדיר את זה ככה אחרי שנון, נראה למה זה פחות או יותר, ואנחנו נגיד, בסדר, זאת ההנחה. זה כמו במכניקה אנליטית, יש לך איזושהי הגדרה של מה זה אקשן, ומשם מתחילים לזרום.
ושאלה אחרונה?
כן.
תיארת את השוטקי המפ הזה?
כן.
למה דעיכה לאפס? לא יכול להיות אם הבנתי.
כי...
אני מבין למה יש דעיכה, אבל
אני אסביר לך. כי האנרגיה, אם תצייר את הדבר הזה כפונקציה של טמפרטורה, היא תלך ותתקבל לגודל קבוע. אז יש לך נגזרת של קבוע, אז זה הולך לאפס. כי זה נגזרת.
כן, זה נכון, זה הבנתי.
בסדר? בגלל שזה נגזרת. עכשיו, אם האנרגיה הייתה עושה הופ, אז הייתי מקבל את זה השני. אז כיוון שאתה מגיע מכימיה, אז נניח יש לי מולקולה, אוקיי? והיא עולה ככה. עולה למעלה, עולה למטה, ואז פתאום אני משובר אותה, ואז עוד אחד.
ההתנהגות הזאת זה התנהגות באמת של באפר של pH.
כן.
האם זה...
כי כל דבר שיש לך, נניח יש לך חלקיק, יש לך כדור, והכדור הוא מתנהג יכול להיות באנרגיה א' באנרגיה ב'. עכשיו אתה מכניס יותר אנרגיה, ואז אתה מגלה, ברגע, בחלקיק הזה, יש עכשיו שני חלקיקים, ואז אתה שובר את האנרגיה הזאת, ואז האנרגיה הכללית עולה. או שיש לך במקום שני מצבי אנרגיה, אתה פתאום מגלה שיש לך עוד אחד שם למעלה. וכן.
הבנתי.
אני לא מבין בכימיה.
זה פשוט בחומציות יש קטע כזה שאתה יכול לשמור את הדרגת pH שלך בגבול מסוים.
כן. אני בערך מבין את זה, אני בערך מבין את זה.
זהו, זה פשוט נראה אותו התנהגות ואני מנחש שזה בא מאותה סיבה של החיבוק הזה.
כן. זה הכל, כמה מצבים אתה פתאום יוצר. כלומר, יש לך המון מצבים, אבל חלק מהמצבים הם לא נגישים. עד שאתה לא נצנח מספיק אנרגיה פנימה לתוך המערכת, המערכת יכולה, עכשיו אני יכול גם לחוות את זה, ואז אתה רואה את העלייה הזאת. ובכימיה, גם בפיזיקה, כל הדברים, גם ספקטרוסקופיה, זה הכל בנוי על הרעיונות האלה. הכל.
תודה רבה.
בבקשה. כן.
רציתי לשאול לגבי אחד, מאיפה שנמשיך מפה, כמובן שאפשר לשנות, כמו שאמרת, אנחנו נשנה את ההנחות שלנו על האנסמבל, אבל למשל במודל שלנו, אמרנו שאין אינטראקציות. עכשיו, אינטראקציות במודל ישנו כמובן גם את האנרגיה של החלקיקים, אבל גם את הסיכוי לנצל?
כן, הרבה פעמים כן. לכן פה אנחנו לא נכניס אינטראקציות. כי נניח אפילו אם אנחנו נגיד שאינטראקציות הן כאלה שכך שהן עדיין שומרות את הסיכויים בכל מצב ומצב להיות אותו הדבר, הבעיה תסתבך. ממש תסתבך, וזה יהיה בעיה. מה שאנחנו נעשה, אנחנו נלך בדרך הרגילה של, בסדר, אנחנו נזניח כל מיני דברים, לדוגמה שהאנרגיה יכולה להיות קבועה, חייבת להיות קבועה, שיש לך איזושהי אינטראקציה עם הבחוץ והאנרגיה עושה פלוקטואציות, וזה יעזור לך לפתור את כל הדברים. זה הצבר הקנוני והצבר הגרנד קנוני. אני אדבר כבר על בעיות אינטראקציה, מה בעצם, איך אנחנו נטפל בהם. יש רק דרך אחת בקורס הזה.
בשאלה נוספת, כשדיברנו על כל הנושאים של עלייה בין המצב האקסייטד למצב יסוד, נראה לי לחשוב על כל מיני חלקיקים לעומת פרמיונים לעומת פוזונים. עכשיו פה יש לנו למשל מציאות מרחבית שהן כל חלקיק שהן גם מרחביות, הם לא נמצאים באותו מקום, אז הם יכולים באמת כל אחד לאותו מצב אנרגטי. אבל האם יש דרך לעשות איזושהי מערכת ככה ש... באמת יש לי מצב כמו למשל בחלקיק כמובן, שאם יש לי אותו מספר של אלקטרונים הם לא יכולים להיות באותה שכבה?
כן, אנחנו נכניס את זה. אנחנו נדבר על סטטיסטיקת פרמי וסטטיסטיקת בוזה, זה חייב להיכנס פנימה, אבל זה חלק מהגדרות המודל שלנו. אתה זוכר שדיברתי, יש לך הגדרות מודל. אז התכונות האלה הן תכונות בסיסיות של החלקיקים, אז כשאני בונה מודל, אני אצטרך להתייחס לזה. ולכן ספציפית לדוגמה פרמיונים שלא יכולים לשבת בדיוק באותה רמת אנרגיה ביחד, אז אנחנו נצטרך לפתח צבר שהוא אפילו לא קנוני, אלא גרנד קנוני. בדיוק בשביל זה הוא נבנה. זה מין דרך לטפל באינטראקציה. כי אם תחשוב על זה, הסטטיסטיקה הזאת זה שפרמיונים לא יכולים לשבת באותה רמה, זה אינטראקציה מאוד חזקה. כי זה לא משנה איפה במרחב, הם מרגישים אחד את השני. אז זאת אינטראקציה. למרות שאני יכול להגיד יש לי פרמיונים ואין להם אינטראקציה, אבל התכונה הזאת אינטראקציה מאוד חזקה וצריך לטפל בזה, ואנחנו נטפל באינטראקציה בעזרת פיתוח צבר חדש. כאילו, אחרי הצבר הזה יהיה קנוני, אנחנו נפתור כמה דברים בצבר קנוני, ייקח לנו זמן, אחר כך אנחנו נגיע לסטטיסטיקה קוונטית, בדיוק בשביל הבעיה הזו של הפרמיונים, ונגדיר צבר גרנד קנוני. כן, זה הרעיון.
מעניין, תודה רבה.
בבקשה.
לגמרי. צערים. כן. עוד לא מרחמי? זה באמת מגעיל, אני ממש מעצבן את זה שעושים את זה שלו אחר. אתה אומר את זה לעצמך או שאתה אומר את זה למישהו אחר? קורא טוב.
איזה נשאר לך?
זה לא באמת היה תלופה, כולי צריכה. כן. כאילו, זה היה תלופה. לא, במידו שאני לקחתי מצדית טוב, זהו, אני אשלח לך את התמונה שלי. חזרתי לבטח, אבל אני אשלח לך את המדינה. לא, תורידי לי. תשיבה.
שלום.
הוא היה שם גם יותר הוא היה הוא מאוד התפלא אותי. הוא אמר לי, וואי, אני נלחמתי בחוק הזה, הוא דיבר גלמים שלי. אז הוא אמר, איך כאילו... כן, הפוך. איך לא הלכת שם למקום כזה, והיית שם במקום כזה. והיינו בתוך מחברת. ועדיין, כאילו, אתה לא יודע. הוא כאילו סיים. מה אתה אומר? כן, מה אתה אומר? זה היה במקום החזי שלי.
זה היה נראה לי ממש לבוש, כאילו ממש תיאור. כן. זה חצי מבחן הזה, אבל מה זה השאלות המסובכות האלה? עינה על העולם. זה הזוי. טוב, אנחנו עושים מבחן.
בוחן.
בוחן, כזה היא עושה כל שני בוחן. אחד גדול מסוג.
מה, אבל עדיף, לא?
סבבה. אבל השאלות האלה, אני לא אעשה זה לא. יש שם איזה קשור שאתה יודע, מישהו שעושה כן נורמלי. לא, לא, לא
אני אחרי זה נגיד תודה, באמת שההחלטה שלה מריצה את זה מהר ואת הדברים החשובים.
מהמרת, אבל לא איזה כיף טבעי.
נהדר, מעניין, אבל...
אני אקח בתור מנחה, כי יש לי ברור לכם. בני, גיליתי שבאפל חום זה גינה זה מה
לא קיבלתי, ואני אומרת לבחורה שהיא אכפת לי אין שיעור, אני חושבת כל שבוע, לא לדבר, אני משקש שלו רשבים ועוד אנשים, סבבה, אפשר ביחד, זה לא מפריע אני יודעת מאוד הקשה בואי פעם הבאה שעשה לי תיסה אותי, אנחנו ישבנו פה טיפסתי אצלי בכל המקום ישבנו פה פה את צריכה מקום שקט שקט פה טוב, איפה אני באה? מה נעשה? לא,
כמעט עוד תקיע.
למה? אתה אמרת שלהם טוב בחורף?
זה... שלום, בסדר. זה המועד אחד של ליברפול ואחד של אוזן. לא בלונדון שלהם קל להגיע. גלסגו בכלל. עכשיו אני גם אישית לי, אחד המועדים ממש בעייתי. ואז לשכנע אותה למועד השני של השפה. כשאז הם הגיעו בלחץ, כאילו נשלחו לעשות מועד במכניקה, כאילו זה יוצא להם לפני המועד הזה במכניקה. נצטרכו כל את שלו, ובכל מקרה זה עדיין כאילו יוצא שהן חוזרות לפני המועד לפני המועד. אז אמרנו להם, תלמדו פה אותם.
היינו כבר בתוך זה.
תציצי גם. נכון. תראי, על רויזן אנחנו מדפנו מלא, רויזי זה אמרו.
אני רציתי להיות בתערוכה
שלנו.
זה עדיין קיים. זה עדיין קיים.
רוצה שנשאר פה עד הסוף ולדבר איתה.
אם אתה רוצה שנשאר כאן.
אני מסתרפה. קיצור תציצי עכשיו.
בתוך הספרייה?
כן, בתוך
הספרייה. אני שואל אותך.
זה מי אמרנו.
לא, רציתי לבוא.
בסדר, היה לך...
זה לא דרך כפר חלקים. מה יש לך?
היי, מה קורה?
מה קורה?
מה קורה?
מה קורה?
אתה יודע שבאתם, נו, נכנסת בסדר? ואת עם בית תחבורה ציבורית?
לא, אני בסוף ברך, אבל הם באו כל כך מוקדם שהיה לי את החניה כבר.
באמת? לרגע אמרתי.
כבר ברגע האחרון.
יש משהו, יש משהו שציפו אלינו, אני מכבד את זה.
כן.
בעבודה שלנו,
כן. קודם כל זה אף אחד לא רואה את זה, רק אני.
בסדר,
לא, יש כאלה שאני מעלה, זה טוב אני לא יעלה.
אתה תעלי? אז נראה איך הוא אמר לי מסתם.
למה? אבל מה כתוב שם? למה מזהה אותם? קראתי את זה לא רע, ראיתי שיש משהו מזהה. שמתם שמות?
לא, אין שמות, לא.
מה זה שמות? לא, אפילו לא כתוב. לא כתוב. לא, אז מה, מכל הארץ? מכל הארץ?
אני
עובר אתיקה.
לא סתם אני קראתי.
קודם כל אני יכולה לא לעלות, ואם אני אחשוב שכדאי לה, אני אקרא את זה עוד פעם. מה זה את שלמה? לא בדקתי? לא ראיתי. כתבת לי שבדקת ששלחת? לא רואה. רגע, אני אתחזק. אתה צריך תמיד, אתם צריכים לא... לא, תמיד תביאו לי, כי אתה הגשת באיחור הרי. רגע, בוא נראה. שנייה, מה נכנס לי לעמדה?
אני חושב שאתה לא יכול לקרוא.
לא, טוב שאמרת לי, בוא דיברנו מאז מלא פעמים. לא, עוד לא סיימתי גם עם זה, אבל כן, שבוע שעבר היה לי בתזות, דיברו אלה שעשו תזות, זה גם נורא נחשב.
אני חושבת לעשות תזה, אבל
אז אני אשכנע מקסימום נעשה שנה הבאה.
אני לא רוצה לעשות מחבר.
אבל הבעיה שלנו... כאילו יש לו באיחור, יש לו באיחור, זה לא בלירן, אפשר לראות שחלקים,
כן.
חכה לצלו של הירן.
לעמדה,
בגלל המילואים, שאולי נעשה רק את הכל
זה מה שמונע ממני להתחיל
לא, גם יבלי הייתי מהבית, נראה לי כן, אני לא מפריעה לי, תראה, גם כשהיא מתחילה לי פה 12, אני אף פעם לא רואה את זה, ואני לא מבינה. רגע, תש"פ סמסטר ב', נכון? פרקטיקה ב'. גם לנו, השנה הזאת הייתה כל כך מבוינת. לא, למה אתה נכנסת אליו מעל זה?